There it is, folks. There it is. There's the number that's causing all this trouble. 2.3, my least favorite number. More on that in a minute. I'm going to do something a little bit different with you guys today. I want to talk a little bit about why we're not in school. We're not in school on Thursday, when school was canceled for the next 3 weeks. There were currently 3 reported cases of COVID-19 in the state of Michigan. There are over 9 million people living here. So why is it that we are not in school? I'm going to walk you through the answer to that question. It has a lot to do with this equation, and it also has a lot to do with calculus. All right, so the first thing is you need to understand that there's only 2 kinds of people that live in this world. Only 2 kinds of people in our population. There's the S's and the I's. Then there's the R's and the U's. Let me tell you about the S's and the I's. They're feeling good. They feel healthy. They think that they're fine. They have no symptoms of this virus. The R's and the U's, on the other hand, they're not feeling so hot. They know that they have contracted this virus. Okay. They know that they're sick. That's a thermometer. Okay. So everyone in our society, the whole population, everybody either feels okay or they don't feel okay. But here's the thing. If you really think about the people that think they're okay, they fall into 2 different groups. The S's. The S's are the people that are susceptible. They actually have not come into contact with COVID-19, or at least they haven't contracted it, and so they are currently healthy, but that means that they are susceptible to contracting the virus. The other group, the I's, they're infected, but they are asymptomatic. Meaning they have the virus, they just don't know it yet. Now let's talk about the people that know that they're sick. It turns out that they fall into 2 very distinct groups as well. See, the R's are the people that woke up and said, you know what, I think I'm sick, I think I have the COVID-19, and they went to the doctor or they went to the hospital, and the hospital gave them a kit and said, yes, you're right, you have COVID-19. So we will call them the people that reported. We have recorded that they are sick. However, a possibly much larger group is the people that are unreported. They know that they're sick, but either the illness is so mild, or they don't have health insurance and they don't think they can afford it, or in the case of one of my Facebook friends yesterday, she went to Beaumont and they didn't have enough tests, so they wouldn't give her one. So there are plenty of people that know they're sick, but they haven't reported the test. Now here's the thing. When we make predictions about how many people are sick and are going to be sick, this is the only piece of information that we actually have. The people that have reported the illness. And everyone else, from the standpoint of a statistician trying to figure out what is happening with this disease, is lumped into the same group. The people that are susceptible and healthy, the people that are infected but don't know it yet, and the people that know they're sick but are unreported. Okay. So let's look at how this relates to calculus and how this relates to my least favorite number. Okay, so check this out. In the beginning, everybody is susceptible because no one has the disease yet. And these susceptible people, some of them are going to contract the virus, and they're going to become the people that are asymptomatic. So once again, these are the susceptibles. These people have the disease, but they don't know yet. So how do people get from here to here? Well, it's transmitted. And how is it transmitted? Well, there's some debate on exactly how it's transmitted, but we know that there is something that is called the transmission rate. Think of the transmission rate as the number of people that can be infected each day by someone that is asymptomatic and doesn't realize that they have the disease yet. Turns out that that number is 2.3. If you're sick and you don't know it, every day you're going to give that illness to 2.3 people, which means that the population of people that are sick is going to more than double. Now, I want to show you some of the rates that are involved in this. So we've got these people that are that don't realize they're sick. Eventually they are going to realize they're sick, and they're either going to become a reported or they're going to become an unreported. And our best guess is that about 25% of people right now are reporting. So I'm going to say that the number of people that go from here is 25% of the asymptomatics, and 75% of the asymptomatics are ending up right here, and once again aren't in the official record. Only these people are getting recorded. Okay. Also, I want you to keep in mind that these people and these people eventually leave the system. They get removed. And in most people's cases, that is because they eventually recover. In some cases, it is because they die of pneumonia related to COVID-19. And so the rate at which people are removed is taking the number of people that are, in this case, reported and multiplying it by the average number of days that they would be sick, which is about 12 days that it takes to recover on average. There's a really wide variation. Some people have recovered in as quickly as 2 days. At the longest, it's taken someone a month to recover. But we'll say that 1/12 of these people are recovering each day. And then the same goes here for the people that are unreported. Okay. Now from there, let's look at how this actually relates to differential equations. The people that are studying this are coming up with models. And I'm going to show you one of their models right here. Here it is. This is a model of the number of people that will be infected on any given day between now and October. And incidentally, this curve is based on us taking no preventative actions to reduce the transmission of the disease. Okay, so I saw this in the paper on Saturday, and I wondered to myself, where did this curve come from? And it turns out it comes from putting together 4 differential equations. First one looks like this. They use the rate at which the number of reporting people is changing. And it turns out that you can calculate that simply by saying the rate is the 25% of the asymptomatics that become reporters minus the 1/12 of the reporters that leave the system. Likewise, our second differential equation is the rate at which the non-reporters are changing, and it's the same idea. They are 75% of the asymptomatics minus 1/12 of them leave the system each day. Now the weird ones are over here. So take a look at the people that are asymptomatic and infected. This is the most important part because these are the people that most easily pass the disease along. The rate at which they change is proportional to the number of people that they have to infect. So there's something that is multiplying S. And that thing that is multiplying S, oh yes, is my least favorite number, 2.3. They get to infect 2.3 of these people each day. Now, I don't want to get too far into the weeds here, but this ends up getting multiplied by the sum of the other people that are not reported in the system. And then we subtract off from that the average time that someone is asymptomatic, which is 3 days. So they are leaving this group at a rate of 1/3 of that population each day. Okay. Finally, right here, the rate at which the susceptible people are changing is negative, because the susceptible people are getting smaller and smaller and smaller as more people become infected. And that equation is actually equal to negative the transmission rate times S multiplied by I plus U. Now, I know that we got a little into the weeds with these 4 equations, but I want you to look at those 4 equations and I want you to think about what we as a society have power over. Do we have power over the rate at which people heal? We don't. Do we have power over whether people report or not? We do a little bit, and so if we could make this number smaller and this number larger, it would to some extent help us mitigate the effects of this virus. But the big thing that we have power over is this transmission rate. Enter social distancing. All right, so the New York Times gives us this graph right here, but they say this is if we do nothing. Suppose we make some interventions, and we've made some interventions, right? Those interventions could be shutting down school. Those interventions could be closing bars and restaurants. Those interventions could be quarantining. The earlier we make those interventions, the less we have people infected at any given time. And that number right there is a big deal, because this number right here has to stay smaller than the number of hospital beds we have available for people in their communities. Also, not only does intervening matter, but the type of intervention that we make is important. So for instance, if we only were to make mild interventions, I would say a mild intervention is washing your hands for 20 seconds with hot soapy water, which you should do. But that is going to have relatively little effect on our transmission rate of 2.3. Modest interventions would be like closing some schools and restricting the size of some crowds. You can see that reduces the number quite a bit. But aggressive steps, which would involve like what Italy is doing, where there's a quarantine going on, you can see that will dramatically reduce the number of infections. Okay, so there it is, folks. Those 4 differential equations are how we figured out that we have this pandemic on our hands. Thank you, calculus.